Okay, so at the previous lecture, we began to discuss commutative Banach algebras. So let's recall that for each commutative unital Banach algebra A, we introduced the maximal spectrum of A, which consists of all maximal ideals of A. We also constructed a bijection between the maximal spectrum and the space of characters, the character space denoted by a hat. So a hat consists of all non-zero characters of A. And the bijection takes each character chi to its kernel. Next, we introduced a topology on the maximal spectrum as follows. So we know that all characters of a Banach algebra are continuous. So a hat is a subset in the dual space A star. So we equip A star with the weak star topology, and we define the canonical topology, the so-called Gelfand topology on the maximal spectrum, to be the restriction of the weak star topology onto a hat. And we proved that this topology makes the maximal spectrum into a compact Hausdorff topological space. And in the end of the lecture, we introduced the main tool of the theory of commutative Banach algebras, namely the Gelfand transform, which is a homomorphism from A to the algebra of continuous functions on the maximal spectrum. And this homomorphism takes each element of our algebra A to a function A hat on the maximal spectrum, where A hat is given by the following formula. Okay, so the Gelfand transform is always a unital, continuous unital homomorphism from A to the algebra of continuous functions on the maximal spectrum. In general, it is not surjective, and in general, it is not injective. In fact, the kernel of the Gelfand transform is so-called Jacobson radical of A, which is the intersection of all maximal ideals of A. So today we specialize to an important subclass in the class of all Banach algebras. Namely, we'll discuss some basic facts on C-star algebras. C-star algebras. So our main goal for today will be to prove the Gelfand-Limerock theorem, which states that if A is a commutative unital C-star algebra, then the Gelfand transform of A is an isometric isomorphism between A and the algebra of continuous functions on the maximal spectrum. Okay, now let's give some definitions. Suppose that A is an algebra. So at this point, it is just an algebra. So it is not equipped with a norm. This is a pure algebraic object. By definition, an involution on A is a map from A to itself, which takes each element of our algebra, little a, to another element denoted by A star, such that the following conditions are satisfied. First of all, this map is it is an involution in the set theoretic sense. That is, if we apply it twice, then we get the identity map on A. Second, just a moment. Second, our map is antilinear. So if we take a linear combination of two elements A and B, then the result will be as follows, where lambda bar and mu bar are just the complex conjugates of lambda and mu. So here lambda and mu are complex numbers, and A and B are elements of our algebra. And finally, our involution is a ring anti-homomorphism. That is, AB star equals B star A star. Now, an algebra equipped with an involution is called a star algebra. Star algebra. Now, by definition, a Banach star algebra. Banach star algebra is a star algebra. Well, first of all, it's a Banach algebra. It's a Banach algebra A. Together with an involution on A. Such that the involution is isometric. That is, the norm of A star equals the norm of A for each element in our algebra. And finally, here's our main definition. You will have a Banach star algebra A. When we say that A is a C star algebra, C star algebra, if the following identity holds, the norm of A star A equals the norm of A squared. This axiom is sometimes called the C star axiom or the C star identity. So it's a kind of miracle that such a simple axiom leads to a very rich and powerful theory. Well, in fact, the theory of C-star algebras is much deeper and much more interesting than the theory of general Banach algebras. C-star algebras were introduced, well, maybe let me say a few words about the history of this notion. So C-star algebras were introduced in a foundational paper of Gelfand and Naimark. In 1943. Well, they used different terminology. So they called such algebras completely regular symmetric normed rings. And the term C-star algebra was suggested by Irving Siegel in 1947. But it was not very popular until 1964, when an important monograph by Jacques Dixmier was published. So after that, the term C-star algebra became standard. So this paper by Gelfand and Naimark was very influential. Well, in fact, some people even say that this paper changed the face of modern analysis. So nowadays, the theory of C-star algebras is one of the biggest and a very rapidly developing fields of functional analysis. So it has many applications in many other fields of mathematics, for example, in representation theory, in harmonic analysis, in operator theory, of course, in algebraic topology, in K-theory, in the index theory of differential operators, in quantum group theory, in quantum physics, and in some other fields. Okay, so these are all objects. Now let's introduce morphisms. Now let's introduce morphisms. So I need the second page. It's here. Okay, so a definition. You will have two star algebras A and B. Then by definition, a star homomorphism from A to B is an algebral homomorphism which is compatible with involution in the following sense. Actually, it commutes with the involutions on A and B respectively. Now, if you have a star algebra A, and if B is a subalgebra A, then we say that B is a star subalgebra. B is a star subalgebra A if it is stable under involution. That is, for each element little b and b, the element b star is also in the same subalgebra B. It's clear from the definition that a star subalgebra is a star algebra itself. And if A is a Banach star algebra and B is a closed star subalgebra A, then B is also a Banach star algebra. In particular, a closed star subalgebra of a C star algebra is a C star algebra itself. Let's now look at some examples of C star algebras. Example 1, well, or better, example 0. The field of complex numbers is clearly a C star algebra. Namely, the involution is just the complex conjugation. So all the axioms of a C star algebra are obviously satisfied. Example 1. If X is any set, then the algebra little L infinity of x of all bounded complex functions on x is a C-star algebra. And the involution here is the complex conjugation. Again, all C-star algebra axioms are readily verified. Example 2. Suppose now that X is the topological space. And let CB of X denote the algebra of all bounded continuous functions on X. The algebra of all bounded continuous functions on X. Clearly, this is a closed star subalgebra in L infinity of X. It's a closed star subalgebra of L infinity of X. And so it is a C-star algebra. This algebra CB of X contains a useful subalgebra which consists of functions vanishing at infinity. So let's give the following definition. If X is a topological space, then we say that a continuous function f on X vanishes at infinity. If for each positive epsilon there exists a compact subset K of X such that f is smaller than epsilon outside K. For example, let's observe that if X is, for example, the set of integers with the discrete topology, or the real line, then a continuous function f on X vanishes at infinity in the sense of the above definition. If and only if it is, well, if and only if it vanishes at infinity in the sense that, in the following sense, if and only if the limit of f of X at infinity is 0. The set of all continuous functions vanishing at infinity will be denoted by C0 of X. Okay, now example 3. Again, if X is a topological space, then it's easy to see that C0 of X, the algebra of functions vanishing at infinity, is contained in CB of X and is a closed star ideal. Is a closed star ideal of CB of X. So it is a C-star algebra. By the way, this C-star algebra is typically non-unital. So a special case is little c0. So little c0 is the algebra of sequences vanishing at infinity. So this is big C0 of n. Of course, an important special case is the case where X is compact. So let's observe that if X is compact, then CB of X equals C0 of X equals C of X. So in this case, the algebra of all continuous functions on X is a C-star algebra. Well, example 4. Example 4. If we have a measure space, X mu, measure space, then it's easy to see that the algebra big O infinity of X of essentially bounded measurable functions, actually equivalence classes of essentially bounded measurable functions, is a C-star algebra. Well, again, the operations are pointwise, and the involution is just the complex conjugation. Okay, so far, all our examples are commutative. The basic non-commutative example, example 5, this is the basic non-commutative example, which serves as one of the main motivations to study C-star algebras, is the algebra of bounded operators on a Hilbert space. So if H is a Hilbert space, then B of H, the algebra of bounded operators, bounded linear operators on H, is a C-star algebra. Now the involution is nothing but the operation of taking the adjoint operator. So let's recall that the adjoint operator of T, where T is a bounded operator on H, is uniquely determined by the following equality. So here all axioms of C-star algebra are, well, I assume they are well known to you from, for example, from the course Introduction to Functional Analysis, which was given in the previous term. This example is very important. In fact, there is an important result in C-star algebra theory, which states that each C-star algebra can be isometrically embedded into B of H for a suitable Hilbert space H. So this is the so-called second Gelfand-Naimark theorem. But we will not prove this result in our course. Example 6. Again, we suppose that H is a Hilbert space. And let's consider the space of all compact operators on H. Well, it's a standard fact that K of H, the set of compact operators, is a closed star ideal. Closed star ideal of B of H. So it is a C-star algebra. And of course, if H is infinite dimensional, then this algebra is not unital. well, let's now give a counterexample or a non-example. Example 7. Let's consider the algebra of n times continuously differentiable functions on the closed interval AB. Well, clearly it's an algebra under pointwise operations. Also, we know that it's a Banach algebra. So let's recall that the standard norm on this algebra is given by the following formula. So this is a standard norm on this algebra, and we know that it makes Cn of AB into a Banach algebra. And it's easy to see that it is a Banach star algebra. Cn of AB is a Banach star algebra. Again, the involution is just the complex conjugation. Nevertheless, a simple but useful exercise is to show that Cn of AB is not a C-star algebra. Oops. Sorry. So it is not a C-star algebra. Of course, unless n is 0. Okay, so here are our basic examples. And now let's discuss some properties of C-star algebras. We start with some algebraic definitions. Suppose first that A is a star algebra. By definition, we say that an element little a of A is self-adjoint. Self-adjoint or Hermitian if A star equals A. Well, more generally, we say that our element is normal. A is normal if A and A star commute. And definition 3, if our algebra is unital, if A is unital, then we say that an element little u of A is unitary. U is unitary. If it is invertible, and U inverse equals U star. Well, let's observe that all self-adjoint elements are obviously normal. and all unitary elements are also normal. And actually, this is the main reason to introduce normal elements. So they are important because they generalize both self-adjoint elements and unitary elements. And one more simple observation is that for each element in A, the element A star A is self-adjoint. Well, this is kind of trivial, but this observation is very useful. So we will use this fact many times. Here's a couple of examples. So, example 1. Suppose that A is the algebra of all functions on a set X, or the algebra of bounded functions on X. So X is any set. Or we can also take the algebra of continuous bounded functions on topological space X. Then it's clear that an element f, so a function f in our algebra, is self-adjoint, even only if it is real, even only if f of x is real for each x. And also it's immediate from the definition that, oops, sorry. So I'm sorry, it seems that I have a little technical problem. Okay, let's continue. So it's also clear from the definition that function f in our algebra is a unitary element, even only if the modulus of f of x is 1 for each x. So in other words, if f takes x to the unit circle on the complex plane. And it's also clear that all elements of our algebra are normal just because the algebra is commutative. Okay, now example 2. An example and an exercise at the same time. Suppose now that A is B of H, the algebra of bounded operators on a Hilbert space. Then it's a useful exercise to show that a bounded operator T is self-adjoint if and only if the corresponding quadratic form given by the following formula is real. Again, something strange is happening. Okay, so let's continue. Well, it's a simple exercise to show that an operator T is self-adjoint, even only if the respective quadratic form, given by the following formula, is real. And a bounded operator U on H is unitary if and only if it is bijective. And preserves the inner product. Well, so at this point, this is a useful exercise, but in fact, we will discuss and prove it a little bit later. So morally, self-adjoint elements can be interpreted as real elements, that is, as analog of real numbers. And the following result, the following simple result, emphasizes this analogy. So I claim that each element in A, for each element in our algebra, there is a unique pair of self-adjoint elements. Unique pair, say, C and D. A unique pair C, D of self-adjoint elements. Such that A equals B plus I. Oh, sorry, not C and D, but B and C. Unique pair B and C of self-adjoint elements such that A equals B plus IC. So B is kind of the real part. B is the real part of A, and C is the imaginary part. Well, the proof is very easy. Actually, these two elements are given by explicit formulas. So B equals A plus A star divided by 2, and C equals A minus A star divided by 2I. So this proves the existence of B and C, and the uniqueness is a simple exercise. Okay, let's now specialize to the case where A is a C-star algebra. So we have the following result. Theorem 1. Suppose that A is a unital C-star algebra. Then for each normal element A, the normal A equals the spectral radius of A. To prove this result, let's first observe that for each self-adjoint element, B in A, the norm of B squared equals the square of the norm of B. This is a special case of the C-star axiom. If we now take an arbitrary element A in our algebra, so we apply this observation to A star A. So we see that the norm of A star A squared equals the square of the norm of A star A. Now, by the C-star axiom, this is the norm of A to the power 4. And we can now write the left-hand side of this equality as follows. So this is the norm of A star A, A star A. But since A is normal, we can write this in the following way. This is A star squared multiplied by A squared. So here we use the assumption that our element is normal. And, well, equivalently, this is A squared star multiplied by A squared. And now the C star axiom implies that this is the square of the norm of A squared. Well, now if we now compare this and this, and if we take the square root of this, we get that the norm of A squared equals the square of the norm of A. So this equality holds for each normal element. Now a simple induction shows that for each natural number n, we have the following equality. And now we can calculate the spectral radius. So the Gelfand formula shows that the spectral radius is the following limit. So this formula holds in any Banach algebra for any element of any unital Banach algebra. Now we can take the subsequence consisting of all numbers of the form 2 to the power n. And it follows from the previous line that this is just the norm of A. Okay, so this completes the proof. Here are some corollaries of this result. Corollary 1. If A is any unital C-star algebra, then for each element in A, we have the following inequality. The norm of A is the square root of the spectral radius of A star A. Well, this is just a combination of the C-star axiom together with the previous theorem. This corollary shows that the norm on any unital C-star algebra is uniquely determined by its algebraic structure. So the right-hand side of this formula is purely algebraic, so it is defined in terms of the spectrum of A star A. So the norm on such an algebra is completely determined by its algebraic structure. As a special case, as a corollary, we see that if A is a unital star algebra, then there is at most one norm on A making A into a C-star algebra. This is immediate from corollary 1. Equivalently, this means that each unit of star homomorphism so equivalently each unit of star homomorphism between unit of C-star algebras is isometric. Well, actually, this result can be generalized as follows. Corollary 3. Suppose that A is a unit of Banach star algebra. And suppose that B is a unit of C-star algebra. And suppose that phi is a unital star homomorphism from A to B. I claim that phi is continuous automatically. And that the norm of phi is less than or equal to 1. To prove this result, let's first take a self-adjoint element. Little a, our algebra. We apply phi, and we observe that phi away is also self-adjoint. And so, by the previous theorem, this is the norm of phi away is the spectral radius of phi away. Well, but phi is a unit of homomorphism, and we know that each unit of homomorphism doesn't increase the spectrum. In particular, it doesn't increase the spectral radius. So this is less than or equal to the spectral radius of A. But the spectral radius of A is less than or equal to the norm of A. So we see that for each self-adjoint element, the norm of phi of A is less than or equal to the norm of A. And if we now take an arbitrary element, A in A, we have the following chain of inequalities. First of all, the norm of, we apply the C-star axiom. So the norm of phi of A squared. Okay, so this was a technical break. So let's now take any element in our algebra A and apply the C-star identity to phi of A. So phi of A sits in the unit of C-star algebra B. And by the C-star identity, we have the following equality. So this is the norm of phi of A star phi of A. Now, since phi is a star homomorphism, we can write this as follows. Phi applied to A star A. Now, A star A is self-adjoint. And by the previous line, we conclude that this is less than or equal to the norm of A star A. And since A is a unit is a Banach star algebra, this is less than or equal to the norm of A squared. And that's it. So this completes the proof. This shows that the norm of phi of A is less than or equal to the norm of A. Okay, so these are the corollaries of the fact that the spectral radius of a normal element is equal to the norm of this element. And now let's look at some properties of the spectrum. Theorem 2. Suppose that A is a unit of C-star algebra. And let little a be a self-adjoint element of A. I claim that the spectrum of A is real. So those of you who attended the course Introduction to Functional Analysis, which was given in the previous term, may remember that we proved a similar result for self-adjoint operators on a Hilbert space. So now we want to extend this result to self-adjoint element of an arbitrary unit of C-star algebra. So to prove this result, we take any element lambda, any point lambda in the spectrum of A. We take any real number t, and we observe that lambda plus it sits in the spectrum of A plus it1. So this holds by the spectral mapping theorem. This implies that the norm, the modulus of lambda plus it is less than or equal to the norm of A plus it1. So we take the squares here and here and use the C-star identity. So by the C-star identity, this is equal to the norm of A minus it1 multiplied by A plus it1. So what is this? This is the norm of A squared plus t squared 1. And by triangle inequality, this is less than or equal to the norm of A squared plus t squared. Okay, let's now write lambda in the form alpha plus I beta, where alpha and beta are real numbers. Substitute it here. So lambda plus it, well, the real part of lambda plus it is alpha, and the imaginary part is beta plus t. So the left-hand side of this inequality is alpha squared plus beta squared plus 2 beta t plus t squared. And this is less than or equal to the norm of A squared plus t squared. Now we can cancel t squared from here. And what we see is that this expression is bounded from above for each real t. Well, of course, this can happen only if beta is 0. That is, even only if lambda is real. And this completes the proof. Okay, now here's a couple of corollaries of this result. So, corollary 1. If A is a unit of C-star algebra, and if chi is a character of A, then chi is a star character. So it's a star homomorphism from A to the field of complex numbers. Okay, to prove this result, let's observe that we may assume from the very beginning that chi is unital. We assume that chi is unital. Because if chi is not unital, then it is 0. First of all, let's take any self-adjoint element, little a, and observe that since chi is a unital homomorphism, the spectrum of chi of A calculated in the field of complex numbers is contained in the spectrum of A. Well, just because chi is a unital homomorphism. But we know that the spectrum of A is real. So the spectrum of chi of A is also real. And this means that chi of A is real. So we see that chi takes self-adjoint elements to real numbers. If we now take an arbitrary element A in our algebra, then we can decompose it as B plus IC, where B and C are self-adjoint. So by the previous result, we see that chi of B and chi of C are real. And so we now calculate chi of A star. So A star is now B minus IC. So this is chi of B minus I chi of C. And since chi of B and chi of C are real, we can write this as follows. This is chi of B plus I chi of C complex conjugate. So this is just chi of A complex conjugate. And that's it. So this means that chi is a star character. The second corollary is about the spectral invariance. So let's recall the following definition. Suppose that A is a unital algebra and suppose that B is a subalgebra of A which contains the identity of A. Then we say that B is spectrally invariant. B is spectrally invariant in A if for each element little b and b, the spectrum of B calculated with respect to the bigger algebra A equals the spectrum of B calculated with respect to the subalgebra B. So let's recall that in the general case, the spectrum of B with respect to the bigger algebra A is contained in the spectrum of the same element taken with respect to the smaller algebra. So if these two spectra are the same, then we say that B is spectrally invariant in A. Equivalently, this means that each element of B which is invertible in A is invertible in B. So we have this equality. Okay, so now corollary 2. Suppose that A is a unit of C-star algebra. And suppose that B is a closed subalgebra, closed star subalgebra, which contains the identity of A. I claim that B is spectrally invariant in A. Okay, and here is the proof. We take an element little b in the subalgebra B and assume that it is invertible in A. So what we want to do is to show that the inverse element sits in the subalgebra B. Well, first of all, we observe that the element B star B has the same property. So it sits in the subalgebra B and it is invertible in A. Now, well, this element is self-adjoint. And so the spectrum of this element calculated with respect to B is real. Therefore, for each non-zero real number t, the element B star B plus IT1 is invertible in B. Okay, so let's now take the inverse element. So what happens when t goes to 0? Since the inversion in A is continuous, we conclude that this element goes to B star B as t goes to 0. Sorry, not to B star B, but to B star B inverse, because the inversion is continuous. But this element sits in the subalgebra B by the previous line. And so, since the subalgebra is closed, we conclude that B star B inverse sits in the same subalgebra B. Okay, let's now look at the following identity. It's clear that B star B inverse multiplied by B star B is 1. Now this is clear, but we now observe that this element here sits in the subalgebra B. So we see that the element little b is left invertible. In the subalgebra B. Now a similar argument applied to the element B star shows that B is right invertible. Little b is right invertible in the subalgebra B. And you probably remember that an element of unital algebra, which is both left and right invertible, is invertible. So we conclude that B is invertible, and this completes the proof. Okay, now we are almost ready to prove the Gelfand-Limburg theorem. Before we can do it, let's recall a classical result from general topology, namely the Stone-Weierstrass theorem. Suppose that X is a compact Hausdorff topological space. And suppose that A is a star subalgebra in C of X. Star subalgebra. Which contains the identity of C of X. That is, it contains the function which is identically 1. And also suppose that the subalgebra A, suppose that A separates the points. Separates the points of X. Then A is dense in C of X. So this is the classical Stone-Weierstrass theorem. I'd like to stress that it's essential here that A is a star subalgebra. So if we work over the real numbers, then A can be just a subalgebra in C of X, which separates the points. But since we work over the complex numbers, we must add the assumption that A is a star subalgebra in C of X. That is, for each function in A, the complex conjugate of this function is also in A. So this is a very essential assumption. Okay, now let's formulate and prove the Gelfand-Limburg theorem. Well, strictly speaking, this is the unital case of the Gelfand-Limburg theorem. Suppose that A is a commutative unital C-star algebra. Then the Gelfand transform of A the Gelfand transform is an isometric star isomorphism. Isometric star isomorphism. Well, first of all, let's show that gamma is indeed a star homomorphism. So we take an element A in our algebra, apply gamma, and evaluate at a point X. Not A, but A star. A star. So what is this? So this is X applied to A star. But we already know that all characters of A are star characters. So this is X of A complex conjugate. And this is nothing but gamma of A star evaluated at X. Here A is an element in our algebra and X is a character. So this implies that gamma is a star homomorphism. And since it is a star homomorphism, it follows that its image, gamma of A, is a star subalgebra of the algebra of continuous functions on the maximal spectrum. Well, it's now easy to see that this subalgebra satisfies the conditions of the Stone-Weierstrass theorem. Because it is a star subalgebra, it contains the function which is identically 1, because gamma is a unital homomorphism, and it separates the points by the very definition of the Gelfand transform. So now the Stone-Weierstrass theorem implies that gamma of A is dense in the algebra of continuous functions on the maximal spectrum. Let's now show that gamma is isometric. So first of all, if A is a self-adjoint element, so for each self-adjoint element, little a, the element gamma of A is also self-adjoint. So the norm of gamma of A actually, it is not essential here that gamma of A is self-adjoint, because we know that for each element in A, the norm of gamma of A equals the spectral radius of A. This is one of the basic properties of the Gelfand transform. But since A is self-adjoint, we see that the norm, the spectral radius of A equals the norm of A. And so we see that gamma is isometric on self-adjoint elements. And now we apply the same old trick. So we take an arbitrary element in A, and we apply the C-star axiom to gamma of A. So this is the norm of gamma of A star gamma of A. And since gamma is a star homomorphism, we can write this in the following way. Well, but A star A is self-adjoint, and we already know that gamma is isometric on self-adjoint elements, so this is the norm of A star A. And finally, about the C star identity, this is the norm of A squared. So this chain of equalities implies that gamma is isometric. And finally, since A is a Banach algebra, we conclude that the image of gamma is closed. So the image of each isometric linear map between Banach spaces is closed. Gamma A is closed in the algebra of continuous functions. But we already know that the gamma A is dense in this algebra. So combining these facts, we conclude that gamma is surjective. And this completes the proof. Okay. Let's now look at a nice category theoretic interpretation of the maximal spectrum and of the Gelfand transform. Category theoretic interpretation. Of the maximal spectrum, of the Gelfand transform, and of the Gelfand-Lambert theorem. So we consider the following two categories. The first category will be denoted by comp. The objects of the category comp are compact Hausdorff topological spaces. The morphisms are just continuous maps. And the second category will be denoted by cuba. The objects of this category are continuous unital Banach algebras. Commutative unital Banach algebras. Commutative unital Banach algebras. And the morphisms are continuous unital homomorphisms. And we now consider two contravariant functors between our categories. Two contravariant functors. The first functor is denoted by sorry. The first functor will be denoted by C. It acts from the category of compact spaces to cuba, and it takes each compact Hausdorff space X to the algebra of continuous functions on X. And if F is a continuous map between two compact Hausdorff spaces X and Y, then C takes this map to the homomorphism which was denoted at the previous lecture by F dot. It acts from C of Y to C of X as follows. It takes each continuous function G on Y to G composed with so these are our first functor. And the second functor will act in the opposite direction. The second functor is denoted by max. It acts from cuba to comp, the category of compact spaces, and it takes each commutative unital Banach algebra A to its maximal spectrum, equipped with the Gelfand topology. Now, if phi is a unital morphism between commutative unital Banach algebras A and B, then our functor max takes phi to the map denoted by phi star, which acts from maximal spectrum of B to the maximal spectrum of A. And phi star acts as follows. If chi is a character of B, which corresponds to the respective maximal ideal, then phi star of chi is chi composed with phi. In other words, phi star is nothing but the restriction of the dual map. Of the dual map phi star, which acts from B star to A star. And we know that the dual of any bounded operator between Banach spaces is weakly star continuous. Phi star is weakly star continuous. So when we restrict phi star to the character spaces, we get a continuous map. So phi star is continuous. Okay, so this is our second functor. So now let's try to compose our functors. So let's recall that let's recall a result from the previous lecture. For each compact Hausdorff topological space X, we have a bijection. Actually, not just a bijection, but a homomorphism. A homomorphism epsilon x between X and the maximal spectrum of C of X. And this homomorphism takes each point little x in our space to the maximal ideal, consisting of all functions on X vanishing at little x. We now have the following proposition. Part 1. If we consider all such homomorphisms epsilon x, so we consider such homomorphisms for all compact Hausdorff topological spaces X. Then the collection of all such maps is a natural isomorphism. Between the identity functor on the category of compact Hausdorff spaces and the composition of Max and C. So these two functors are isomorphic. Part 2. Let's now consider the Gelfand transforms of all commutative unital Banach algebras. So here A runs over the class of objects of the category cuba. Well, I don't claim that this is a natural isomorphism, but at least it is a natural transformation. From the identity functor on cuba to C composed with Max. And finally, we have the following result. This is part 3. There is a natural isomorphism between the following two Hom functors. First functor is the Hom functor in the category cuba from A to C of x, where x is a compact Hausdorff space. And the second functor is the Hom functor in the category comp from x to max of A. And explicitly, this natural isomorphism looks as follows. If we have a Banach algebra homomorphism from A to C of x, morphism phi, then the respective continuous map from x to max of A looks as follows. First, we apply epsilon x, which acts from x to the maximal spectrum of C of x. And then we compose it with phi star. Sorry, not. Yes, of course. So epsilon x acts from x to the maximal spectrum of C of x, and phi star takes it to the maximal spectrum of A, to the maximal spectrum of A. And the inverse map, which acts from right to left, looks as follows. If F is a continuous map from x to max of A, then the respective homomorphism from A to C of x looks as follows. First, we apply the Gelfand transform, gamma A, which acts from A to the algebra of continuous functions on max of A. And then we compose it with phi dot, and the resulting map acts from A to C of x. So this is, I claim that this is a natural isomorphism. Here A runs over the objects of cuba, and X runs over the class of all compact Hausdorff topological spaces. And to make this even more transparent, let's replace the category comp by the dual category or the opposite category. And so this is nothing but the set of morphisms in the dual category comp opposite from max of A to X. So this picture means that the functors max and C form an adjoint pair. This is an adjoint pair of functors. The proof of this result is absolutely straightforward. So I'll leave it as an exercise for you. Well, actually, this exercise is optional because I don't assume that all of you are familiar with the language of category theory. But I hope those of you who are familiar with this language will agree with me that the proof is very easy. Okay, and let's now consider one more category, which will be denoted by CUC star. Objects of this category are commutative unital C star algebras. Morphisms are continuous unital star homomorphisms. By the way, we already know that all unital homomorphisms between C star algebras are automatically continuous. So I can take the word continuous to in brackets. They are automatically continuous. Well, proposition two. So now we consider our two functors as functors between the dual of the category of compact Hausdorff spaces and the category of commutative unital C star algebra. So the functor C acts from here to here, and the functor max acts from here to here. I claim that these two functors are equivalences of these two categories. So in other words, the category of compact Hausdorff topological spaces is dual to the category of commutative unital C star algebras. And moreover, the respective adjunction isomorphisms look as follows. The identity functor on CUC star is isomorphic to to C composed with max. It is isomorphic to C composed with max by means of the Gelfand transform. And the composition of max and C is isomorphic to the identity functor of comp, that is, or more exactly to the dual of comp by means of the isomorphism epsilon. So this result, again, the proof is very straightforward, so I'll leave it as an exercise for you. So this result is a classical example of a complete duality between algebra and geometry. So a topological category of compact topological spaces turns out to be a dual to the category of commutative unital C-star algebras, which has an algebraic origin. And this fact leads directly to non-commutative geometry in the sense of Kohn, of Alain Kohn. So the fundamental principle of this part of non-commutative geometry is that each non-commutative unital C-star algebra can be considered as the algebra of continuous functions on a non-commutative compact topological space, which doesn't actually exist. Well, this may seem paradoxical, but this strange point of view leads to a very deep and interesting theory, which has many important applications. In fact, many topological constructions, many pure topological constructions, after we translate them to the dual language, have analogs for arbitrary, that is not necessarily commutative, unital C-star algebras. For example, the classical K-theory of compact spaces is completely embedded into the K-theory of C-star algebras. Well, in conclusion, I'd like to say just a few words about the non-unital case. The non-unital Gelfand theory. There are many important reasons to consider non-unital algebras. First of all, many Banach and C-star algebras which arise in applications are non-unital. For example, the algebra of compact operators on a Hilbert space is not unital, and also the group C-star algebra of a non-discrete locally compact group is also non-unital. Also, there are several important constructions, for example, stabilizations and suspensions, which play an essential role in K-theory or C-star algebras, and which always produce non-unital algebras. Non-unital C-star algebras also naturally appear in applications to representation theory, to harmonic analysis, and to the quantum group theory. On the other hand, non-unital algebras are not very essential for our introductory course. So I'll give you only a survey of the respective theory. So suppose that A is a commutative algebra. A commutative algebra, not necessarily unital. It turns out that in the non-unital case, the set of all maximal ideals is no longer relevant. We should consider only those maximal ideals which have the following property. So let's say that an ideal I of A is modular if the quotient of A modulo I is unital. Or equivalently, this means that there exists an element U in A such that A minus AU sits in I for each element A in our algebra. This U is an element whose class modulo I is the identity in the quotient of A modulo I. So the collection of all maximal modular ideals is denoted by max of A and is called the maximal spectrum of A. So the maximal spectrum is the collection of all maximal modular ideals. Well, exactly as in the unital case, this set, the maximal spectrum, is closely related to the character space. So the character space, the space of all non-zero characters, is denoted by A hat. And we have a canonical map from A hat to the maximal spectrum, which takes each character chi to its kernel. So it's easy to see that the kernel of each non-zero character is always a maximal modular ideal. So exactly as in the unital case, we have the following important result. If I is any proper modular ideal of A, then it is contained in a maximal modular ideal. There is a maximal modular ideal J of A such that I is contained in J. So it's important to stress that for non-modular ideals, this result fails. So it's essential here that the ideals are modular. And the proof is very similar to the unital case. So we just replace the identity of the algebra by the modular identity little u for the ideal I, and repeat essentially the same argument. Okay, now coming back to the above map from A hat to the maximal spectrum. First of all, we can observe that it is always injective, precisely as in the unital case. And if we assume now that A is a Banach algebra, then we have the following result position. First of all characters. So, well, first of all, let's assume from the very beginning that A is a commutative Banach algebra. Well, that A is a commutative Banach algebra. Then, first of all characters of A are continuous. All characters of A are continuous, and actually they are contained in a closed unit ball of the dual space. In fact, here it's not essential that A is commutative. The first part of this proposition holds for each Banach algebra, not necessarily commutative. Second, all maximal modular ideals of A are closed. And finally, the above map from A hat to the maximal spectrum is a bijection. Okay, so now we identify these two sets, I mean the maximal spectrum and the character space of A, and we can introduce a topology on the space in more or less exactly the same way as in the unital case. So a hat sits in the dual space, A star. We equip A star with the weak star topology. And we define the canonical or the Gelfand topology on A hat, which is identified with the maximal spectrum, to be the restriction of the weak star topology onto this set. An essential difference here with the unital case is that the space, the maximal spectrum, is no longer compact. Well, indeed, when we proved the compactness of this set of the spectrum, we essentially used that our algebra is unital. Nevertheless, if we add only one point, namely the zero character, then the set of all characters, including zero, is closed in A star. Moreover, it is closed in the closed unit ball of A star, and so it is compact. So this chain of inclusions implies that A hat is a locally compact Hausdorff topological space. And in general, it is not compact. So here's a basic example. If X is any locally compact Hausdorff topological space, for example, the real line, then we have a homeomorphism epsilon between X and the maximal spectrum of the algebra C0 of X of continuous vanishing ad infinity functions on X. So we see that even for C0 of X, the spectrum is not necessarily compact because it is homomorphic to X. Now, if A is a commutative unit, is a commutative but not necessarily unital Banach algebra, then we can define the Gelfand transform of A in much the same way as in the unital case. But now the Gelfand transform acts from A to the algebra of C0 on the maximal spectrum, to the algebra of continuous and vanishing ad infinity functions on the maximal spectrum. The construction of this map is exactly the same as in the unital case. And now the Gelfand-Naimark theory, the Gelfand-Naimark theorem for commutative C-star algebras looks as follows. If A is a commutative C-star algebra, then the Gelfand transform of A is an isometric star isomorphism. An isometric star isomorphism between A and the algebra C0 on the maximal spectrum of A. So this is the general form of the commutative Gelfand-Naimark theorem. Well, very briefly, the idea of working with non-unital algebras and of proving such results is to consider the so-called unitization of A. So if A is a non-unital algebra, then the unitization of A is defined as follows. We take the direct sum of A and the one-dimensional space spanned by a new element 1 plus, and we define the multiplication on this algebra in such a way that this new element 1 plus becomes an identity of this algebra. So this is the multiplication in this algebra. And A plus, this algebra A plus, is called the unitization of A. It can be shown that if A is a Banach algebra, then A plus is also a Banach algebra. And a slightly more difficult result is to show that if A is a C-star algebra, then there is a canonical norm on A plus, which makes A plus into a C-star algebra. And here's a picture now which relates the Gelfand transform of A with the Gelfand transform of its unitization. So the Gelfand transform of A acts from A to C0 on the maximal spectrum. And the Gelfand transform of A plus acts from A plus to the algebra of continuous functions on the maximal spectrum of A plus. Well, it can be deduced from the above discussion that the maximal spectrum of A plus is homomorphic to the one-point compactification of the maximal spectrum of A. So here, plus means the one-point compactification. So this is the Gelfand transform of A, and this is the Gelfand transform of A plus. Now A is a codimension 1 ideal in A plus, and the algebra C0 on the maximal spectrum of A becomes a codimension 1 ideal in this algebra, in the algebra of continuous functions on the one-point compactification of the maximal spectrum of A. Actually, a function on the maximal spectrum of A vanishes at infinity, if and only if it extends to the algebra, if and only if it extends to the maximal spectrum of A plus, and this new function vanishes at the infinite point. And this diagram is commutative. So basically, the Gelfand transform of A becomes the restriction of the Gelfand transform of A plus. And so the above general form of the Gelfand-Naimark theorem really follows from the unital case. And probably that's all I wanted to say about the non-unital case. And so this is the end of today's lecture.